Must be clear.
This is Mark III, Electron Linear Accelerator at Stanford University. Instrument for nuclear research, 300 feet long, a city block. Soon to be dwarfed by a machine more than 30 times its size, designed to probe the atomic nucleus to help reveal the worlds within. To learn about matter, a never-ending, increasingly difficult quest. As man learns more about the world around him, his unknown world shrinks in size, and he must develop more complicated instruments to study it. A paradox. Larger instruments to study smaller things. The microscope to study the living cell, 1/1000th of an inch in diameter. The electron microscope to study a virus, 1/1,000,000th of an inch in diameter. And the high-energy accelerator to study the atomic nucleus, 1/1000th of a billionth of an inch in diameter. So small that trying to see it with rays of light would be like trying to determine the size and structure of a grain of sand by feeling it with boxing gloves. Yet for 50 years, physicists have examined it, and measured it, and weighed it, and have learned of its structure. A structure made up of incredibly small particles, each containing smaller ones. Electrons, protons, neutrons. Only these were known 30 years ago. Now there are positrons, antiprotons, mesons, pi mesons. Over 30 have been discovered, as instruments have been developed to reveal still smaller particles. How is it done? The high-energy accelerator, or atom smasher, provides the means to see what cannot be seen. There are many accelerators of varying sizes and types. All operate on the same basic principle: to shoot small subatomic particles into targets of atomic nuclei and to see what happens. In order for these particles to penetrate the nucleus of the atom, they must possess very high energies. They are given very high energies by accelerating them to almost the speed of light. The machine that does this is an accelerator. Some are circular in shape. Europe's 14-nation research center in Switzerland, Brookhaven National Laboratory in New York, Lawrence Radiation Laboratory, University of California, Argonne National Laboratory, Illinois, and the Soviet Union's Nuclear Research Center in Dubna. Another type accelerates particles in a straight line, the high-energy linear accelerator. If the accelerated particle is an electron, it is called a high-energy electron linear accelerator. The first practical version was developed at Stanford University in 1947. It accelerates electrons through a straight copper pipe to subatomic targets at the end. An electron gun, much like the one in a television tube, provides the electrons, projecting them into the copper pipe or waveguide. To provide the energy necessary to accelerate the electrons, high-powered radio wave amplifier tubes called klystrons are used. Invented at Stanford by Russell and Sigurd Varian, klystrons were first employed during World War II as radar tubes. In the electron linear accelerator, klystrons inject bursts of energy into the waveguide kicking the electrons faster and faster until they are traveling at almost the speed of light. The target is the atom. Since most of the mass of the atom is in the nucleus, only 1/100th of 1,000th of the diameter of the atom, most of the electrons pass through without hindrance. But some electrons do hit the nucleus and are deflected. Sometimes an electron, as it slams into the nucleus, dislodges or even creates new particles, fleeting, evasive building blocks of matter. The size and shape of the nucleus is determined by studying the pattern produced as the electrons are deflected at different angles. Its composition is revealed by these patterns and by the new particles formed on collision. Usually, the data consists of numbers, but counting numbers is one thing. Translating them into an orderly understanding of matter is quite another. The physicist's exhausting task of theoretical analysis. The decade-old 300-foot-long Mark III accelerator in its academic environment at Stanford University is a very useful instrument of basic research. Scientists, students, engineers, teachers have come to Stanford from all parts of the world to work with the eminent physicists who have developed and utilized this electron linear accelerator. Physicists like Professor Hansen, who completed 2 machines and started construction of the present Mark III before his death in 1949. His successors, Edward Ginston and Wolfgang Panofsky, who have continued the development of the electron linear accelerator. Professor Robert Hofstadter, who in 1961 was awarded the Nobel Prize for his work in performing the most precise measurements ever achieved of the size and shape of subatomic particles. But on this occasion, Dr. Hofstadter stated the problem.
There must be very delicate orbits in there, well-defined properties which can be discovered. You need clarity, better focusing.
Better clarity, better focusing, to reveal more detail than is possible with the Mark III. The solution was obvious. Build a bigger, more powerful instrument. Professors Panofsky, Ginston, Moseley, and many others conceived the plan to build an accelerator 2 miles long, 30 times the length of Mark III. For more than a year, they worked on their proposal to build the largest device of its kind, to establish a research facility available to scientists throughout the world. The proposal was presented to the Atomic Energy Commission in April 1957. In 1959, President Eisenhower announced,
I am recommending to the Congress that the federal government finance the construction as a national facility of a large new electron linear accelerator. Physicists consider the project, which has been sponsored by Stanford University, to be of vital importance. Because of the cost, such a project must become a federal responsibility.
In 1961, Congress authorized $114 million for construction of the Stanford Linear Accelerator Center. Work could now begin on the 5-year task of building one of the largest, most powerful instruments ever created to study the smallest particles of matter. To build such an instrument takes people, men and women eminently qualified in their respective fields. physicists and engineers with the specialized knowledge to design and build klystrons, metallurgists, technicians, and craftsmen to assemble and test the 10,000-foot copper waveguide. Model makers to assemble the complex structure in miniature. An administrative staff to coordinate the budgets, schedules, and changing requirements. These people must build a copper tube 4 inches in diameter, containing a copper disc every inch, 2 miles long, and absolutely straight.
We start with a very special kind of copper, about 1.5 million pounds of it. Because of the very, very pure copper required for these various operations and for the disc-loaded waveguide and waveguide themselves, we have set up and are operating an unusual copper metallurgy laboratory. The copper gets formed into various shapes, rings, cylinders, and the like. These machined rings and discs are then put together into a 10-foot length. After stacking the various discs and cylinders, we move it on into the brazing furnace, where we then make a 1 10-foot length accelerator section.
The world's most powerful klystrons must be designed and built.
The project, and we concentrated on tubes that were intended to have about 25 megawatts of peak power and about the same average power in kilowatts, or 25 kilowatts. Physically handling them is a real problem. The tubes aren't necessarily big, they're heavy. A tube with all of its accessories will probably weigh somewhere in the neighborhood of half a ton. So we have had to design a different tube, if for no other reason than to cut down weight, make them simple, easy to connect, and as trouble-free as we possibly can make them. In the beginning, we'll use 240, and we'll divide the power over the 2-mile length of the accelerator. A vacuum tube of this sort is essentially a mass of geometric shapes which are all tied together and impervious to the outside atmosphere. The structure, the internal structure and its shape is the thing that actually makes the tube. Here a fingerprint, for example, contain enough free ions, molecules, to cause a good deal of trouble, so that people who are handling these components that make up the tube and the vacuum system associated with it, they have to be extremely careful. We're handling a very high-powered pulse. A single pulse represents a nominal operation at 250,000 volts, represents 66 million watts. A large amount of power, I think, by any standards. We say, for the length of a pulse, we want 66 million watts. Well, the length of our pulse happens to be very, very short. The power pulse to the tube, to cause it to operate, lasts between 3 and 4 millionths of a second.
We are making provisions that the different pulses coming from this machine will alternately be directed to different target areas. This is being done by what we call pulsed magnets. That means magnets which can be turned on very quickly and can be turned off very quickly, which bend the beam into the one area or the other.
Experiments must be planned that will use the electron beam as the accelerator is brought into operation.
One thing which is being done in many of the establishments we are planning to do is to have a substantial number of experiments set up and in readiness. So we believe that during a given period of time, there might be as many 10 or 15 experiments in the works, so to speak.
A structure must be built to house the accelerator. In reality, 2 structures. First, a concrete housing 2 miles long under 25 feet of earth to contain the 10,000-foot 4-inch diameter copper pipe, the heart of the accelerator. And second, a 2-mile-long building on top of the ground to house the accelerator's klystrons and auxiliary equipment. Buildings must be erected for the tools to construct the accelerator and for the people who will operate it. These buildings must be designed to blend aesthetically into the rural landscape at minimum expenditure of taxpayers' dollars.
Just to put some numbers on it, we're moving about 2 million cubic yards of earth to make a level base and cover for this accelerator. We'll also need about 100,000 cubic yards of concrete for shielding and construction purposes.
We really want to maintain this as near its original natural state as possible, just like it looked before we came on the scene. And of course, when you get 2 miles of dead level straight lines, this is real difficult to do. So you've got to use landscaping and earth and plant it and be discreet in the uses of fences and roads so that the impact is as small as possible.
The Board of Trustees have considered this as a part of the campus, although the end station buildings will be virtually a mile from the quadrangle. The trustees are still looking at this as being a part of the Stanford University campus.
The red roofs and the wide overhangs and the sandstone coloring, the shadows on the wall, are all in sympathy with the existing campus. In fact, this is a campus within a campus. The attempt here is to provide an environment that is both productive and pleasant in support of a research facility. One of the things that helps us is that these buildings are nestled down in knolls of earth about 35 feet high.
The actual accelerator is under the Earth's shield, and it's simply physically impossible to get to a place where there is any acute radiation hazard. We have established standards of radiation control which are more stringent than any of the standards of any laboratory now existing in the United States. It's very much more conservative, in fact, than the minimum standards prescribed by the government.
The largest and most expensive research tool in the world in a pastoral setting where people come and go as they wish.
This device, of course, is not a military establishment in any sense of the word. On the contrary, it is an open research tool. We will publish everything that goes on. The product of these accelerators is knowledge. What the nation is investing in this accelerator and the contribution which Stanford is making in terms of its lands are used to buy knowledge and fundamental understanding of nature.
knowledge, and the fundamental understanding of nature, products of the greatest quest in man's history. To search for truth, to forge new paths into the minute jungle, so small that most of it has not yet been conceived in the minds of man.